So we established in the last video that there are many sets, infinitely many sets, that have the same cardinality. And so it helps to give some kind of a name to this cardinality, to this infinity, so that we can talk about it and distinguish it from others if they exist. Now, in calculus and other areas of math, you might have seen this symbol, sort of like a sideways 8, to represent the concept of infinity, but that really means something different in the context of limits and integrals. It's a way of saying that something is sort of getting arbitrarily large, which means something a little bit different than what we're talking about here when we're talking about how many elements are in a set. So when we talk about the size or the cardinalities of sets, we're dealing with what we call cardinal numbers. And we often identify a finite cardinal number, let's call it k, with the set of natural numbers from 1 to k, because this is a set that has cardinality k, that has k members. Now, when we're talking about the cardinality of the set of natural numbers, which we've shown is equivalent to the cardinality of the integers and the rational numbers, we refer to this as this symbol here. You'd pronounce that as aleph naught. Aleph naught. Right, aleph is just a Hebrew letter, capital Hebrew letter, with a subscript of 0. Pronounce that as aleph naught. That is, it's the first infinite cardinal number. Now, we haven't exactly proven yet that there are others, but we will eventually show that there's, in fact, infinitely many infinite cardinal numbers. The first one being aleph naught, as we said, followed by aleph 1, on aleph 2, and so on. You have one for every natural number k. There's an aleph k, and then eventually others as well, so I'll just sort of describe it as aleph sub alpha for now, and more. Okay, so it turns out that there's many different sizes of infinity, infinitely many different sizes of infinity. Now, it's maybe worth pointing out that at a very basic set theoretic level, even defining sets as, say, the set containing 1, 2, 3 can be kind of a problem, right? What does 1, 2, and 3 even really mean? And so behind the scenes, we're really defining natural numbers in kind of a weird way, where we say that, for instance, we're identifying the natural number 0 with the empty set, or sometimes we use that symbol for the empty set, and then we kind of recursively define any larger natural number by saying that for a natural number n plus 1 is just n union with the set containing n. And so that would give us something like, well, 0 is equal to the empty set, 1 is equal to the set containing the empty set, 2 would be equal to the set containing the empty set as well as the set containing the empty set, right? Because that's sort of like saying this is like the set containing 0, and this is the set containing 0 and 1, and so on. But really, right, we're thinking about these as cardinalities, and like I said, we often identify a set of numbers based on the cardinality of the natural numbers up to that point. And so we can think about the number 1 as being the cardinality of the set containing the empty set, 2 as being the cardinality of the set containing the empty set, along with the set containing the empty set. 3 is the cardinality of the set containing the empty set, and the set containing the empty set, and this set here up above in number 2, or the number 2, so the set containing the empty set and the set containing the empty set. And we start to see how this can get very cumbersome to talk about and to write about. And so once we've really established these finite cardinals, we just use the symbol 0, 1, 2, and 3, and so on to make things a little bit easier to talk about. Right, so this is a little bit of background information that is maybe fun fact, but we'll just use the natural numbers when we're talking about these. All right, so it turns out that we can add, we can multiply, we can do other operations on cardinal numbers, even the infinite ones, just like we do with natural numbers and other real numbers. But we have to define them a little bit carefully. So we want our finite cardinal arithmetic to work the same way that it would for natural numbers, right? So if we want to say that 2 plus 3 is equal to 5, then we need to give some sort of justification for that using sets, because remember, this 2, 3, and 5 are representing cardinalities. Now, this makes sense, for instance, if we say that the set A is equal to the set containing 1, 2, and 3, and the set B is equal to the set, containing 4 and 5. Because if that's the case, then we would have that the cardinality of A plus the cardinality of B is equal to the cardinality of A union B. The union of two sets is when you just take all the elements of the two sets, squish them together into one big set. So that would be the cardinality of 1, 2, 3, 4, 5. And therefore, you would get this equation. 2 plus 3 is equal to 5. The cardinality of A plus the cardinality of B is equal to the cardinality of the union. Well, that's great. And that works as long as A and B are disjoint sets, because principle of inclusion-exclusion would tell us that the cardinality of A plus the cardinality of B is equal to the cardinality of union. That doesn't work if the sets are not disjoint. In other words, it doesn't work if A and B, if those two sets have some elements in common. So for instance, if A is equal to the set containing 1, 2, and 3, and B is equal to the set containing 1 and 2, then again, we still want to make sure the cardinality of A plus the cardinality of B is equal to 3 plus 2 or 5, but taking the union doesn't really help here because A union B, we're not getting any new elements. We're just getting 1, 2, and 3 back again, right? We don't want to count 1 and 2 again as extra copies. And so the cardinality of that union is just equal to 3 in this case. And so we don't necessarily want to just use unions to help us try and determine the addition, right? Addition of cardinalities. So instead, we use a different definition of cardinal addition as follows. So we say that the cardinality of A plus the cardinality of B is the cardinality of the following set. I just realized I missed an absolute value bar here. It's a cardinality of the set containing ordered pairs of the form A, 0, where A is an element of the first set A, and then elements of the form B, 1, where B is an element of the second set B. So let's just test this out and make sure that it worked in our last example, where A was the set 1, 2, 3, and B was the set 1, 2. We want to make sure that the cardinality of A plus the cardinality of B is actually 5. And indeed it is, because this set on the inside of the parentheses, or inside the absolute values here, is going to be the set all elements of the form something in A, 0, so 1, 0, 2, 0, 3, 0, and then all elements of the form B, 1, where B is in B. So 1, 1, and 2, 1. And yes, the cardinality of this set, the number of elements, is just the number of ordered pairs. 1, 2, 3, 4, 5. Right, very good. That's what we wanted. And so we can see that this is going to give us addition of finite cardinals that corresponds to the addition of those corresponding natural numbers. But what about for cardinalities of infinite sets, right? What happens if we add two infinite cardinals together? Do we get a new infinity? Well, let's try it out with an example. So remember, we say that Aleph naught is the smallest infinite cardinal number, and it corresponds to the cardinality of the natural numbers. What would Aleph naught plus Aleph naught be? So by definition, Aleph naught plus Aleph naught is going to be, again, missed some absolute value bars here. It's the absolute value of the set of all numbers of the form, or the set of all ordered pairs of the form n, 0, where n is a natural number, along with n, 1, where n is a natural number. So essentially, it's basically, the cardinality 1, 0, 1, 1, 1, 2, and so on. And then after infinitely many of those, we now switch to, I did that wrong, sorry. My y-coordinate stays fixed as 0. So 1, 0, 2, 0, 3, 0, and so on. Followed by, now we keep our second y-coordinate of fixed at 1, so we'd have 1, 1, 2, 1, 3, 1, and so on. And the size of this infinite set is going to be this, what we call Aleph naught plus Aleph naught. Is that really a different cardinal than Aleph naught? Well, it turns out no, right? Hilbert's Hotel tells us that if we have, one set of natural numbers, or one infinite set indexed by the natural numbers, and then another infinite set indexed by the natural numbers. So imagine a full hotel, and then another number of infinitely many guests indexed by the natural numbers show up. We were still able to accommodate them, right? So no, this is not a different infinity. This is the same infinity all over again, and we can we can sort of prove this a little bit more carefully by saying there is a bijection between, or from n to that set up above. Like, let's just, for the sake of ease of notation, let's call that set A, as follows. So what we can do is we can say that let f of n map to n over 2, comma 0, if n is even, and let f of n be equal to n plus 1 over 2, comma 0, if n is odd. Oops, sorry. N plus 1 over 2, comma 1, if n is odd. In other words, the even-numbered natural numbers are going to map to this whole set of ordered pairs, and then the odd natural numbers are going to map to, the odd natural numbers are going to map to this set of ordered pairs here. All right, and we can prove in the exercises that this function is in fact a bijection, but what that tells us then is that the cardinality aleph naught plus aleph naught is in fact equal to aleph naught again, right? Maybe, it's sort of a surprising thing, right? So when you add at least these particular two infinities together, these two smallest infinities together, you just get that same infinity back again. Now, that's not necessarily always the case, and in particular, if you add together two infinities that are both infinite but different sizes of infinite, you would need to use the axiom of choice for this, which we'll discuss in the next section, but if at least one of two cardinal numbers, kappa and gamma, are infinite, then it turns out that the sum, kappa plus gamma, is just going to end up being equal to whichever one of those cardinalities is bigger. So the max of kappa and gamma. All right, now cardinal arithmetic, or cardinal addition, does have some nice properties that we also enjoy in natural number arithmetic. It's associative, so if you have kappa and gamma, that was a lambda. Kappa, lambda, and gamma. Adding kappa plus lambda and then adding gamma to that is the same as, those aren't even kappas. Getting my Greek letters all mixed up. Kappa, lambda plus gamma is equal to kappa plus parentheses lambda plus gamma. We have that it's commutative, which just means for any cardinal numbers, kappa and gamma, kappa plus gamma is equal to gamma plus kappa. It has identity 0, so if you add kappa plus 0 or 0 plus kappa, you get kappa back again. This is true for all cardinal numbers, kappa, lambda, and gamma. These are some sort of nice properties that addition has for cardinal numbers. Now, we can define multiplication for cardinal numbers as well. So we can say that given sets A and B, we could define the product of the cardinalities, A and B, to just be the cardinality of the Cartesian product, which is to say the product of these two cardinalities is going to be equal to the cardinality of the set of all ordered pairs of the form A comma B, where A is an element of the first set A, and B is an element of the second set B. All right, so we can check pretty easily that this is going to give you the same kind of, the same kind of multiplication that you would expect for finite cardinals. So you can check pretty easily that when A is equal to the set containing 1, 2, and 3, and B is equal to the set containing 1, 2, that the cardinality of A times the cardinality of B, 3 times 2, is actually going to give you the same cardinality as A cross B, the Cartesian product of those two sets. But what about for infinite cardinals? So again, if we wanted to try and compute aleph naught times aleph naught, we need to find the cardinality of this Cartesian product. So this is right here is n cross n. Right, this is what we're trying to compute. The cardinality of n times the cardinality of n and it should be the same as the cardinality of the Cartesian product n cross n. Now again, Hilbert's Hotel kind of gives us some intuition here already, because we proved in section 2.2, exercise 2, that if there's countably many, let's say buses filled with countably many guests each, we had it sort of indexed by the prime numbers, that there is a bijection, or from n to n cross n. In other words, we could accommodate infinitely many copies of infinitely many new guests in the hotel. That these cardinalities are in fact equal to each other. And again, we want to be a little bit more careful here with a bijection, but we can find a bijection, we can define a bijection f from the natural numbers 2n cross n as follows. So what we'll do is, we'll say, given a natural number n, we'll map it to the ordered pair x comma y, where x and y are the unique natural numbers that satisfy the following equation. N is equal to, 2 to the x minus 1 times 2y minus 1. So this might seem like it kind of came out of nowhere, but the idea is that any natural number can be expressed as a product of an even number, in fact, not just an even number, but a power of 2, times some odd integer, or some odd natural number. Every natural number has a unique way of being expressed this way. So just to give you a couple of examples, we would say that f of 1 under this function is going to map to 1 comma 1, because we can express our input 1 as 2 to the power of 0 times 1, or 2 to the 1 minus 1 times 2 times 1 minus 1. Right, and so the 1 comma 1 here comes from this exponent, and then this coefficient here. Similarly, we could have that f of 2 is equal to, we would want to map that to 2 comma 1, because we can express 2 as 2 to the power of 1 times 1, or 2 to the 2 minus 1 times, 2 times 1 minus 1, and so on. And of course, we would have to actually prove that this is a bijection that's well defined and that it is a bijection, but you could prove that as an exercise, and that shows us that the set of natural numbers has the same cardinality as n cross n, or n many copies of n. Now, this tells us that aleph naught times aleph naught is in fact equal to aleph naught, right? Now, once again, the axiom of choice is going to allow us to show that if at least one of the cardinalities, kappa and lambda, is infinite, then, and as long as neither of them is equal to 0, then again, the product of kappa and lambda is just going to be the max, right, whichever one is greater, of kappa and lambda. Now, again, we have some nice properties that are analogous to properties of natural number multiplication. Again, it's associative and commutative. It also distributes over addition. So if you have cardinals, kappa, lambda, and gamma, kappa times lambda plus gamma is equal to kappa times lambda plus kappa times gamma. And similarly, if we were to multiply on the right, we also have the multiplicative identity of 1, so kappa times 1 is equal to 1 times kappa is equal to kappa for all kappa, and the property that kappa times 0 and 0 times kappa are both equal to 0. So cardinal arithmetic works pretty nicely, right? It has a lot of the same properties that natural number arithmetic has, and this seems to answer the question of whether infinity plus infinity or infinity times infinity is bigger than infinity, right? It seems to suggest that the answer is no, at least for cardinals. In the next video, we'll see that maybe that's not necessarily always the case.